So good morning. This is a lecture of computer control on parameter estimation using least squares. And you probably remember that we were considering the problem of introducing the least squares principle for estimation. And we solved a very simple problem, which was to fit a straight line to experimental data. So suppose that you have an experiment and you have two quantities, x and y, and you want to relate these quantities by a linear model, y equal to alpha x, and you want to estimate alpha. Now, what happens is that due to deviations of your theory, the model does not fit completely the data, so the relation is not perfectly linear. Y is not exactly alpha x. If alpha was alpha x, you could say, well, alpha is just y and x, so give a value to x and estimate the value of alpha or compute the value of alpha by y divided by x for that experiment. But actually, this is not so. So one possibility is to use the principle of least squares. So you assume your model and you have a number of data. So x1, x2, and y1, y2, and so on are numerical values for that correspond to the results of the experiments you did on your system. And now you find an alpha such that this sum of squares of deviations is the smallest. So you write what we call a least squares functional associated to alpha. Okay? This is nothing more than a quadratic function of alpha. And you see that this is a sum of squares of deviations between what you observe for y, that's y subindex I, and what you were expecting yi to be given the value of xi, which is alpha xi. Okay? This is according to the model, yi should have this value, so this deviation should be 0. But it is not due to experimental errors and measurement errors and so on. So what you do is you try to find out alpha that minimizes this sum of squares. Okay, and okay, of course, this is a quadratic function in alpha, so this is a parabola, and you are looking for the value of alpha that minimizes this parabola. So you differentiate j with respect to alpha. See, if alpha is just one parameter, then it's just a total derivative, and you equate this derivative to 0. You can multiply by a factor, because if you multiply on the left by a factor, you are on the right multiplying 0 by a factor is still 0. So 1/2 is a good choice because it simplifies the computations. We have seen that. And you compute the derivative and you equate to 0 and you solve this system of equations. Okay? And then I made a remark which is important, which is, does alpha correspond to a minimum of the functional? Well, you should look at the second derivative, and the second derivative is the sum of the squares of the independent variable. Okay? This is what I call, in more general situations, persistency of excitation condition. That is to say, the data has to be rich enough for you to be able to compute alpha. In this case, it is enough that at least one of values of x is different from 0 for you to have a minimum. Of course, the more data you have, the biggest the accuracy in estimating alpha. Now, in the end of the lecture, I place this problem. So you let an object to fall down, and you measure for a different number of times elapsed from the beginning from the moment in which the object starts to fall down. You measure the distance that the object traveled due to gravity. Okay? And we believe that this law that corresponds to constant acceleration holds. Okay, so the distance traveled is proportional to the square of t. Now, there is dependency on the square of t, but the dependence on g is linear. So you can think as that your independent data is t squared divided by 2 for different values of t, and the dependent data is the corresponding values for h. Okay, and e is the other deviation. So I put it here, but actually I do not use it when I do the computation. So I said that probably someone could be brave enough to use 1 minute or a couple of minutes to show the solution of these problems. Is there a volunteer among you? It is wise never to be a volunteer. But if you are in the army, okay, if you are in the army or in the corps of firemen, never be a volunteer. But here it's good to be a volunteer because you will have the extra possibility of training your capacity of speaking in the audience. So no volunteers? Okay, I will just show the functional, and the estimate is just to differentiate the functional with respect to g and equate it to 0. So the functional, you can see it here. Okay, I wrote it just for the first 3 points. Can you see my? Let me show my screen. So I will unshare, stop sharing. Okay, can you see?
Yes.
Yes, Professor.
Yeah.
Thank you. Thank you. Thank you. It's an important help that you tell me that you give me some feedback. So what we have, I just wrote for the different points the value, the distance, and the distance that would be expected given the value of g that I leave as a variable. Okay, so if I have just one of these terms, g is just equate this term to 0. But now I have several terms and I have to compatibilize these. So I add more terms and I have the square of the deviations. I wrote it just for the first 3. Okay, of course, in a real problem, sometimes you have thousands of data, so you have to use a computer. And so this is a quadratic function in G. And you have then to differentiate it and equate it to 0 to get the estimate for G, the least squares estimate for G. Bear in mind that the estimate is not necessarily the true value. Actually, what we mean by true value may not even exist. I mean, we think about nature in terms of models, okay? And what happens is that we can have models that fit the behavior that we are observing. When I say nature, I see a technical process or an economical process or biomedical process, okay? And we have models, and we try to fit the models with the data that we have. And so a criterion is least squares, and we use this criterion. Okay. Any question? Okay, so I will share my screen again. Where is it? It's here. And now we move to another problem, okay? To another problem that are actually related to what we want to study in this course, which is control. So I want to model a system defined by a difference equation. Imagine that I have this difference equation that you see here that relates the input of a system U with the output of the system Y. And I observed a series of numbers taken at even intervals of time. So that's the sampling instance. And I also observed Y at the same instance. Okay? And I want to estimate the parameters A1, A2, AN, B0, B1, B2, Bn. Okay? And this is an estimator. So it's a kind of inverse problem. You can think of the system, usually you think of the system associated to this problem. I know U, I know the systems, so that's knowing the A's and the B's, and then I want to compute Y. But now, instead of computing Y from the system and from the input, we are solving another problem, which is given a pair of U and Y that I observe, I want to estimate the parameters of the system. Okay? This is an important first step in design because you need these parameters if you want them to design a controller. So what you see is data. Okay? So you do an experiment, you get data for U and Y in the form of lists of numbers. In MATLAB, you can use a vector of numbers for U and a vector of numbers for Y. And you want to estimate the A1, A2, etc., B0, B1, etc. Okay? The parameters that define the system. So let's start by considering a very simple example and use the least squares principle. So suppose that your system is first order. So your model is y of k plus 1 equal to a yk plus b uk plus some noise. Okay, this noise models things like stochastic disturbances that act on the system, or observation noise, so noise associated to sensors. It's lumped here in E. So what we expect is that E to be small and to be random in the sense that it is uncorrelated. So if you observe E1 and E2, these are stochastic variables, the random variables that are not correlated. So you cannot get information on E2 by looking at E1. Okay, so this goes up and goes down and goes up and goes down in a way which is random. Later, we will characterize better the properties of this. I call it noise, process noise. Now, I do a number of observations for U and Y. Okay, I apply, for instance, a square wave or any other signal to U, and I observe the corresponding Y. Okay, and I want to estimate A and B. Okay, this is my model. And assume that we have, since we have the data for Y and U, so you can compute these quantities. Yeah, they're a little bit mysterious, but in a moment we are going to see that we need them. And what we do, in a normal situation, this is a parenthesis, in a normal situation, I would give you some minutes to solve this problem by yourselves, but here I will do it right away. So I will apply the principle of least squares. So what am I going to do? I'm going to write the functional, the least squares functional, which is the sum for all points of data, so I have capital N points of data, of the output minus what I expect the output to be given the model. So the model is dynamic. So here I have y of k plus 1, and here I have what I expect y of k plus 1 to be. That's minus a of yk plus b of uk. Okay, that's why we have these two minus here. Okay. Remember the model. The model, if you forget about e, which is this small random number that measures deviations of the model, then y of k plus 1 minus ayk minus buk should be close to 0. Okay, if this is close to 0, this should be close to 0. So the least squares functional is this quantity. It's a quadratic function now of two variables, a and b. Okay, and you want to minimize this quadratic function with respect to a and b. You want to select a and b such that this quadratic function is the smallest possible. Now, what you do, you know from analysis that you have to compute the partial derivatives of j with respect to a and with respect to b. Okay, and you have to equate them to 0. And this gives you a set of two linear equations that you can solve with respect to estimates of a and b. Okay? Now, a number of details. I had here 1/2, so you can multiply your functional by any factor that is different from 0, of course, and you will get the same results for a and b, for the estimates of a and b. So I've selected 1/2 because when I compute the derivative of the sum is the sum of the derivative, so I can interchange the derivative sign with the summation sign. Then I have a square, and this would give 2 times the basis, which is this term here, times the derivative of the basis with respect to a and with respect to b, depending on which the derivative I'm computing. Okay, so this square cancels with this 1/2, and this simplifies a little bit the expression. So I end up with these two system of equations. Now I use some properties. I use some properties of the sum and distributive property of multiplication. So the sum of this term is the sum of yk plus 1 plus the sum of yk squared, and a goes, it's a constant, so you can take it out. It's common to all the terms. You can take it out of the summation and so on. Okay, so I end up with this system of equations here. I placed a hat to emphasize that the variables a and b that satisfy this system are nothing more than estimates. They are not the true values of a and b, but they are the estimates. Now, if I know the data, I can compute these summations here. In this case, I end up with this term, and then I solve the system of equations. I hope you know how to solve a system of equations, a linear system of equations, of algebraic equations. And I get the estimates of a hat and b hat. Okay. Now, I could give you an example with 3 variables, and we had to add an extra partial derivative with respect to the third element, solve another problem, then another one and another one. So by Christmas, we would probably be able to solve problems of 20 by 20 parameters. But this is not practical. So in order to proceed and to estimate, to have formulas to estimate an arbitrary number of parameters, are there any suggestions?
We could use matrix notation.
Matrix notation, that's very good, okay? That's very good. So that's where what we are going to do. We are going to write this using matrix notation, and actually everything will be very simple. We end up with a formula for the least squares estimate. Before doing that, is there any question that you want to make about this example? I've omitted a number of passes here, so my suggestion is that you complete later, when you study this slide, you do all the details, you complete all the details, which is nothing more than algebra. Okay, so to use matrix notation, let's suppose that we have this difference equation, okay? Don't forget that E is here because it's just to remind us that we have some deviations with respect to the true. The model will never exactly fit the true data. So what am I going to do is I'm going to express y as a linear combination of the previous y's and the previous u's. So I define what I call a regressor, okay? And the regressor, I call it, this is the Greek letter. This is the Greek letter phi, and the regressor has all the data that you have, okay? Then I'm going to define vector of parameters to estimate. Then I put there all the A's and B's, okay? And now I'm going to write the difference equation in this form here. So yt is phi transpose. Phi transpose is this row vector, okay? Minus yt minus 1 minus t equal minus 2 minus t minus y of t minus 3 and so on in use. And this is, so I multiply phi transposed with theta. Theta is a column vector because theta transpose is a row vector. So theta is a column vector with a1, a2, etc. So remember that when we multiply matrices, we do multiplication of lines by column. So we have a line here in phi transpose multiplying the elements of the column theta, okay? And given this definition of phi transpose, the prime means transposed, okay? And theta, so given these two definitions, this is a compact way of writing this equation. Before we proceed, does everybody agree with this? Understand how I passed from representing the difference equation to the so-called linear regression model? Is it clear for everybody? If it is not clear and you don't say anything, you are dummy.
Professor, just a question.
Mm-hmm.
The B shouldn't start in B0 in theta?
Yes, that's right. So I should have had it B0. Thank you very much. That's a mistake I have here. So B0, B1, etc. So B0 multiplies U of t minus 1. So it should start in B0. Thank you very much. It's a misprint. Good. More questions? No. Yes, yes. A word about this expression, a regressor. Regressor means to go back. So you are expressing y of t in the previous values of y. So you are going back in a sense. That's why we use this expression. Actually, this is a standard expression from, or expression standard term from statistics. And this is the linear regression model, or the linear regressor. So you can when you express one quantity as a linear combination of other quantities that you know, you put the known data in phi prime, phi transpose, prime, remember, is transposed here, and you collect all the unknown parameters that you want to estimate in theta. Okay. Now, this model is very general, much more general than the use of representing difference equations. For instance, if you have just two quantities that you want to relate by some model, and you want to estimate the theta, you can write this model if you are able to, if the dependence is linear on theta. And this is valid even for nonlinear systems. Suppose that I had here squares of u or any other function. But imagine that the yt was depending on the square also of some values of u. So I would add them to the regressor and I could start writing the first thing. So what is critical here is that the dependency on theta is linear. Okay, so theta do not appear as complicated functions, but just as the multiplication by the values of theta. Okay, so first step, write the difference equation as the linear regression model. Okay. Now, my least squares criteria is the sum for all points of data. So I call capital N the number of data points of y of t minus what I expect y of t to be. So given the linear regression model, y of t should be theta transposed phi. Oh, here I had phi transpose theta. So another mistake or no? Is this correct? Or not? Remember, y is a scalar. So a scalar is equal to itself transposed. Now, if you transpose y, you are transposing phi transpose theta. And the transpose of two matrices is the transpose of the product of the matrices inverted. So transposing phi transpose theta is the transpose of theta times the transpose of phi, which is phi. Okay, so you can write either theta transpose phi or phi transpose theta, and you get the same result. Because in this case, this gives you a scalar. Okay, in general, this is not true. You cannot interchange the product of matrices. But these are vectors, and it's a line and a column, so you get just a scalar. Okay. Now we have our famous 1/2. Okay, we are familiar with that. But then I have added. I have divided by the number of data. What is the convenience of writing by the number of points of data? Does anyone suspect or has some suggestion? It does not affect the result. So why would I place here and then?
When we have a lot of data, we don't want the function to be really big, so we divide by n. Maybe.
I could not understand the last sentence. Can you repeat it, please?
If we have a lot of data, n is really large, so our function would have a big value. So we divide by n to have like a mean value.
It's like a mean value, that's right. Okay. So later we will be interested in doing parallels with the expected value of the deviation. Okay. And this is the mean value. Okay, is the mean value of the functional, and later we will compare it with the expectation, so the mathematical expectation, which is a different thing, but it's related, of course. Very good. Now, what I do is I want to estimate, let's go back. I want to estimate theta from observations of y and phi because, well, I don't measure phi, but I measure the entries of phi. The entries are the elements of phi. Okay, so I know y and phi, and I have theta. So I could say theta is y divided by phi prime. Why can't I say that? Suppose that I don't have any error. Okay, so E is 0. So Y is exactly phi transposed times theta. And I'm telling you, well, why not to do a theta equal to Y divided by phi prime? Why is this not possible to be done? If you don't want to speak in English, say in Portuguese and I will translate, okay?
Phi prime is a vector.
Phi prime is a vector, and so?
You can divide.
You can't divide by a vector. We don't know how to divide by a vector, okay? Does not have an inverse. So what we do is we observe a number of data, okay? And so for t equal to 1, I have phi prime of 0 theta plus the noise and so on. For t equal to 2, phi prime of 1 theta and so on, okay? Now, I can write from the first equation, I can write a second equation. So what is the mathematical argument that allows me to write a second equation? Be careful. Why are these two equations equivalent? Because here I have theta, here, 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 and here I have theta just outside the matrix. So no ideas?
Maybe because it's linear.
Okay, that's a dangerous. It's tempting to say that, but it's not. It's not true. I mean, when you say linearity, you say that you apply the distributive property, isn't that, of multiplication with respect to summation. So if I multiply theta by phi 1 plus phi 2, that's phi 1 theta plus phi 2 theta.
Yeah.
But that's not. It's not what you are doing here. You see, what you are because. This is a matrix. I mean, it's not a parenthesis. So you are not applying distributivity. What you are just using is the definition of matrix multiplication. Okay, so look at the second set of formulas. How do you do this product of this matrix? This is a matrix. Each line of the matrix is one of the phi transpose at 0, at 1, and so on. So you multiply the first line by the first column. And here you just have one column. So you multiply phi transpose of 0 times theta, and you get the first element. Okay, that's what you have there. Then you multiply the second line by the first column, and you get phi transpose of 1 times theta. You get the second element, and so on. So this is just matrix multiplication, okay? So we have this matrix here, this matrix equation here, okay? And I will call capital phi to this matrix made of data, y bar to this vector of y's, again data, theta, well, that is our vector of parameters, and then I have some epsilon bar, which is a vector of deviations. Now, suppose that you don't have any deviation here. Now I have a matrix. So could I say that theta is the inverse of phi multiplying y bar?
No, because you have the error.
suppose that you don't have any errors. So your model perfectly fits the data. So epsilon bar is not here, okay? Epsilon bar is not here. Can I say that theta is phi, the inverse of phi times y bar? I give you a hint. For which type of matrices do you know how to compute the inverse? Para que tipo de matrizes é que sabem como calcular a inversa? Yes?
Symmetric. Symmetric.
Symmetric? Just symmetric?
No, not symmetric, but there's a property.
Square matrices.
Square matrices, okay? Square matrices. So, what can you say about the story of theta being the inverse of phi times y bar?
You can compute.
N must be equal to NP.
So the number of data must be equal to the number of parameters. That's reasonable. Okay. So if the number of data points is equal to the number of parameters, then you can write theta as phi transposed, phi inverse times y bar. But now you have this story of the noise. Okay. So if you have the noise, sometimes the noise goes up, sometimes the noise goes down. So how should capital N be with respect to the number of parameters? What is a wise choice?
And capital N must be a lot bigger.
Bigger than what?
NP.
The number of parameters, NP. Okay. So if you have noise, okay, you want to have more data points than parameters to estimate. Okay? A colleague of mine a professor of chemical engineering, he says, well, I can model a camel with a square function, with a quadratic function. But if the function is cubic, I even can model, and apart from the camel, I can model the tail of the camel. Né? Ele diz, se eu tiver uma função quadrática, eu modelo a bossa de camelo. Mas se a função for cúbica, além de modelar a bossa, ainda modelo o rabo do camelo a abanar. Okay? So, the question is that you want to have a lot of data points, and from all those data points, you want to say the average behavior of the system. Okay? So this matrix is not squared. When you have noise, this matrix should not be squared. And you should have more data points than parameters, much more data points than parameters. Okay? So in a sense, we are going to learn how to solve this equation for non-square phi. That's the least square solution. Okay. So let's write our least squares functional in this way. So look here at the bottom. Okay, look here at the bottom. Again, I have something missing. There should be a transposed here. So y bar. Look at here. You can see my pointer. My hand, the hand in the slide. Can you see it?
Yes, Professor.
Okay.
Yeah.
Thank you. So look here. Y bar minus phi theta is a deviation. Okay, that's a deviation, and this is a vector of deviations. Okay. Now, if you compute the same vector but transpose, there is a transpose missing here. Okay, should be another transpose. This is the transposed vector of deviations times the deviation vector itself. So this is a sum of squares of deviations. And then you multiply by 1/2, 1 divided by 2n. Now, if you expand this term, don't forget to transpose, you get this thing. So remember that the transpose of the transposed is the oh, okay, this is correct because I'm transposing everything here already. Okay, this is correct. So you see that this is the transpose of that. So I'm not putting there the transpose. I'm already putting it in here. So now you apply the non-associative and distributive properties for multiplication of matrices. So you multiply this term by this term and this term, and this term by this term and this term. So you get everything here. And then you should be careful because this is a scalar. J is a scalar. So when you multiply theta transposed, phi transposed by y bar, okay, this is a scalar because you have here this element is a row, this is a matrix, and this is a column. So you end up with a system which is with a final result which is a scalar. And so when you compute, you can transpose it, and that's the same of multiplying y bar transpose times phi theta. That's why I have just two of these elements here. You see? So this times this gives you this. This times this gives you this. And then you have the cross products, which I just lumped in place of 2 here. Okay? Using the property that the result is a scalar, so it's equal to its transpose. Now, I want to find out the value of theta that minimizes this quantity. So what can I do? I will compute the gradient. The gradient, that's a vector of partial derivatives. And we know a number of properties for the gradient. In particular, if you have a quadratic function of x, this is a general result. X transpose ax, that's a quadratic function of x. Okay, A is a matrix. And you compute the gradient with respect to x, that's 2x transpose A. Okay. Now, you apply the gradient to J with respect to theta. What happens? Well, this is a constant, so the gradient of something times the constant is the constant times the gradient. Okay. Gradient, remember, is a vector of derivatives. Now, the gradient with respect to theta of y bar transpose y bar is just 0 because this do not depend on theta. Now you have here something, a vector that multiplies theta. Now, if you have a vector that multiplies theta, the gradient is just this vector. Okay, so minus 2 y bar transpose phi. Okay, this is a vector. And now here you apply this rule. So remember that my A matrix is phi transpose phi. Okay, and my X is theta. So I have 2 X transpose, which is theta transpose, and then matrix A, phi transpose phi. So my gradient is given by this. So I can cancel the 2. I can even multiply everything by n to get rid of this. And I repeat it here. I repeat it here. I have this minus. Okay. I have this minus. So I add this term on the left to cancel it, and on the right. So I end up with this system of equations. Now, this system of equations is on theta transposed. So I transpose everything. If I transpose everything, remember, when I transpose a product, I have to transpose the elements and put it in the reverse order. So I start with phi transposed times phi transpose, which is phi here, and times theta hat transpose, which is theta hat. And here I have phi transpose times y bar transpose, which is y bar. I'm changing the order, okay? So what do I have here? What do I have here? I have a matrix, okay? And this matrix is square and with the dimension of theta hat. If you look at theta, theta is n by np, and so this is np times n, and this is n by np, so this is np by np. So you have a matrix with a dimension of theta hat equals to, and this is a vector with a dimension of theta hat too. Okay? So you have a system of equation in which theta hat is the unknown, the vector of unknown. So if the inverse of this matrix exists, you can write theta hat as the inverse of this matrix times theta transposed, phi transposed y bar. Okay? So you can write, you can reach this conclusion. What is this conclusion? If you have the linear regression model, okay, and you can write this matrix phi by making the elements of phi transpose to be the elements of this matrix phi. So this matrix is, remember, built in this way in slide 159. Okay. Then the vector of estimate satisfies this equation. This is a set of algebraic, linear algebraic equations. We call it the normal equation. Okay. Now, if this matrix phi transpose phi as an inverse, then you can write your estimates in this way. Okay. Now, if you have as many parameters as data points, phi, capital Phi is square, and you have what? You have the inverse of phi times the inverse of phi transposed. That cancels with phi transpose, so theta hat is just phi inverse times y bar, the result that we know. So when we have as many parameters as data points, but in general, we have more data points than parameters, and this matrix phi has more rows than columns, but this phi transposed phi is still square, and you can still compute theta in this way. So this is a kind of inverse. We call it the pseudo inverse. Okay, that's a name we want, but it generalizes to non-quadratic or non-squared matrices, the notion of inverse. Questions? So to come here, what we did, we wrote the quadratic functional, we applied the gradient, we equated the gradient to 0, and we solved the equation, which is gradient equal to 0. So we end up with this, then we transpose just to, we end up to this, okay? There is a transposition in between. And then if this is invertible, then you write the equation in this explicit form. If this is not invertible, for the data you have, it means that we have several solutions for the parameters that explain the data that you are observing. Questions? Are you completely lost? You want me to repeat something? Go back?
It's fine, Professor.
Okay. Okay. So you can still, when you study the slides, come back and answer things and ask questions, sorry. Okay. Now, we have this story of inverting the matrix phi. what are the conditions that you think that you should impose so that this capital phi is invertible? You have any idea? Let's see this example. Suppose that you want to estimate, this is a system, it has a delay, and apart from that you have a zero. Okay, so 1k is just a linear combination of the previous two values of u. Okay, and you have some noise. So suppose that u is constant. Can you estimate, you do a lot of observations of y in u. Is it possible, if u is constant, to estimate b0 and b1? What do you think? Suppose that u is always 1, always. Again, if you don't feel comfortable speaking in English, speak in Portuguese.
I don't think it's possible, Professor.
You think you think it's not possible?
Yeah, I think it's not possible.
Why?
Because we have to dos incógnitos e só temos uma equação.
We have two unknowns, b0 and b1, and u is constant. So y is b0 plus b1 times 1 times the data. So how can we, all the equations that we observe is just, are always related to b0 and b1, to the sum of b0 and b1. Okay, if u is constant. So what would you do to estimate b0 and b1? Not just their sum. You could do a different experiment. What experiment? In one experiment, u is constant. Can you think of another experiment so that you can estimate b0 and b1?
Maybe u is 0. For example, u is 1 from uk minus 1, but in uk minus 2, it is still 0.
So alternating between zeros and ones. Okay, that could be
Yes.
work. Okay. So you have to change u. Okay. So you have to excite the system. Okay? This is an extreme situation. If you write phi in this situation, then you would come to the conclusion that this matrix, this big matrix phi, is all the rows are equal if u is equal to 1. Okay, so it's a good exercise that you should do, and that's why you end up with something which is not constant. Okay, so sorry, you end up with something that is not invertible. Now, if u changes, you are giving some excitation to the system, and that allows the phi matrix to be inverted. Okay, these in general are the so-called persistent excitation conditions. I mean, you could write a book just on persistence of excitation conditions. There are results that says, for instance, with least squares, you can estimate in linear systems, you can estimate a number of parameters which is equal to the number of points in the frequency domain where the spectrum of u is not 0. For instance, if you excite a system with a sinusoid, okay, or with a, then you would be able to estimate 2 parameters, because the sinusoid is non-zero at 2 points in frequency, one positive and one negative. Okay, so you can estimate 2 parameters, and so on. So when you do experiments, and this will be of practical importance in your when you are doing your let's call laboratory work. So your laboratory project, which is not done in the laboratory, it's just simulation, but it's the same. Then you should be able to excite the system enough. Okay. Sometimes a square wave, it's not the best choice. You should have, there are other signals, and Professor João Pedro Gomes will speak more about to you in the tutorial sessions. For instance, the PRBS, which is a sequence that appears to be random, but actually it is deterministic. And it has the advantage of being reproducible, okay? And it's much better than a square wave, just a square wave. One thing which is very bad is to use a constant, a step. Why is a step a bad estimate, a bad choice for exciting the system? You apply a step. A step is 0, 0, 0 up to the initial instant, and then 1, 1, 1, 1, 1, 1. Why is the step not a good choice?
Because there will be rows in phi that will be equal, and we end up with a matrix that cannot be invertible again.
It's invertible, but it's not. I mean, among the you can think of the conditioning of the matrices, and matrices can be close. Their determinant can be close to 0, so it's difficult in practice to invert a matrix. According to your intuition, Jose, what do you think it happens? That's a mathematical result, but what happens according to our intuition? If we apply a step, when are we exciting? At what time are we exciting the system?
When the step is applied,
When the step is applied, that's right, when it changes from 0 to 1, but then it stays at 1, you see? So after there is a transient, but that's it. And then it stays close, it's a constant. You are exciting the system with a constant after a while, okay? So that's a very poor excitation. A constant is a kind of sinusoid which is which has zero frequency, okay? That's a little bit a crazy thing to say, but it's true. So your excitation is very small with a step. Okay? With a square wave is a little bit better because every now and then you are having some transient, you are inducing some transient. But the best thing would be something that changes a lot. You should be careful with the bandwidth of the system, because if you are changing things too fast, the system does not correspond, does not respond, is not able to follow very high frequency changes. Okay? So within the bandwidth of the system, dentro da banda, da largura de banda do sistema, you have to excite it a lot. Okay? If you have something which is slow, then you cannot apply a very fast signal. Okay? You have to match your excitation to the type of signal that you have. But within those bounds, you should have a lot of excitation for the parameters to be, for your algorithm to be able to estimate your parameters. Okay. Now, a couple of notions that will be quite important in the future. One is the notion of error covariance matrix. So I define P, the error covariance matrix, is the expected value of, you see, this is the error. Okay, this is the error. This is the true value of parameters theta, and this is the estimated. I put a hat to say it's the estimate. So this is the error, the deviation between the estimate and the true value for theta. And this is a column, and this is a vector. So this is a matrix. Okay, this is not a scalar. A scalar would be if I place here the transpose. So this is a matrix. Actually, symmetric matrix. This is a symmetric matrix. In the diagonal elements, I have what? I have the in the diagonal elements, I have the power, that is to say, the expectation of the squared values of the deviations of the parameters. When I speak here of deviations, are the deviations of the parameters, not of the output. Okay, so this is in the diagonal. I have the squares of the estimation errors, and off the diagonal, I have the elements which are the cross correlation of the errors of estimation. Now, let's speak a little bit about the story of the E. So I'm assuming that my Y is this linear combination of parameters plus some noise E. Okay, and if E is a wide sequence, okay, what is a wide sequence? What is a wide sequence? A wide sequence is a sequence that has no memory. It's a sequence of random variables that are independent for each other. Okay, let me give you an example. Can you see my hand? Can you see my hand?
Yeah.
Okay, so this is my sequence E. Okay, each of my finger is one element. So E equal to 0, T equal to 0, T equal to 1, T equal to 2, and so on. So E of 0, E of 1, E of 2, E of here. I only have 5 fingers, so I can go only up to E equal to 5. Now, I replicate my hand. So, okay, I replicate my hand. I replicate the data, okay, my sequence. Now, if I multiply my sum and my my polish and my indicator and my medium and so on, each one by each other, and then I add everything, I have the sum of the squares of the values of the noise. That's the power of the noise. That's the autocorrelation of log 0. Okay. Of course, this gives you some number which is bigger than 1, apart from the fact in which E is 0. If E is 0, you get 0. But if E is not 0, okay, if it is a random variable, then you get some number. That's the power of the sequence, okay, or the variance of the sequence. Now, shift it a little bit. So my polish, you see. So this one goes with this one and so on. So my sum goes with the indicator, no pulgar vai com o indicador e por aí fora. Okay? And then you do these products and you add everything. You have the autocorrelation of log 1. Okay? If you sum these things and if you compute the average, now suppose that your sequence of numbers is independent. So if it is independent, my polish is independent from my indicator. So when I do this multiplication, I'm multiplying two independent random numbers, and the expectation of the product is the product of the expectations. Since each of them has lag 0, you get 0. Okay? So a wide sequence is a sequence such that the numbers are formed by a sequence of random variables that are independent from each other. Okay? And when you do these computations, you get, for lag 0, you get the power of the signal. And for any other lag different from 0, you get something which is 0. Okay? That's white noise. So it's a sequence that has no memory of itself. Now, if your noise is a white sequence, and white sequences are going to appear many more times in the future, if your noise is a white sequence, then least squares behaves very well because the estimate is unbiased. That is to say, the expectation of the error is 0, or this means that if you enlarge the data set in which you are basing your estimates, this is going to be closer and closer to the true value theta, the estimate. And the variance, if the variance or the power of the white sequence, or the variance of the random variables that form the white sequence is 1, then P is given by this value. Okay? So you can compute the error covariance matrix by picking up your matrix of data and doing this computation here, the inverse of phi transpose phi. Okay, these are two important properties. If your sequence is not white, then you have to multiply here by a scaling factor that depends on the noise. Okay. Now, the error covariance matrix is the inverse of phi transpose phi. So I define a matrix called lambda, which is the inverse of the covariance error covariance matrix, and I call it the information matrix. Okay, if I have large P, the inverse will be small. So if I have large P, I have a large error, and I have little information about my parameters. If my error covariance matrix is small, okay, then the inverse of a small number is a large number. Actually, these are matrices, but okay. And then I have a lot of information. I have a lot, my information matrix is large, okay? And the information matrix is related to phi transpose phi. Okay, actually, these are nothing but words at this moment, but you can relate this matrix information, this information matrix with other concepts related to information theory. Okay. So remember these two concepts, the error covariance matrix and the error covariance matrix and the information matrix, which is its inverse. And also remember that if your noise is a white sequence, least squares are very well behaved. But if not, the first property is not true. Okay, so the expectation of the error is not 0, but your least squares estimate will be so-called biased. Se o ruído não for branco, a estimativa de mínimos quadrados vai ser o que se chama polarizada. Okay? Now, you can say, why to bother about studying least squares? We should study other methods. We are going to see that, in particular in adaptive control, sometimes even when we have the so-called colored noise, non-white noise, least squares have an interesting property that two errors compensate for each other, and then you converge to the optimal gains of the controller. Okay, that's a self-tuning property that we are going to see later. In addition to that, least squares are a very simple and low computational algorithm to compute. Okay, low computational algorithm to apply. So they have a lot of advantages, and if you use it properly, you can avoid this problem of having non-zero error. Okay. Now, what we are going to do next, and we will speak tomorrow, is at this point we have a so-called batch solution. So I receive a number of points and I compute the solution. If I receive another point of data, I have to do everything from scratch. What we are going to study next is a recursive solution in which, instead of redoing everything from scratch, when we receive a new data point, we combine this new data point with the previous estimate to update the solution and to have an algorithm which is very efficient from the use of data. Questions?
Professor, just a quick question. When we are talking about noise that is not white, are we talking about outliers in the data, or are there any other?
Outliers is a different thing. Outlier is a non-Gaussian noise. Okay, it's a heavy tail noise. So an outlier is something that appears, it's a large deviation that appears with a high probability. Okay. When you have Gaussian noise, the noise follows a Gaussian sequence. And of course, you can have large deviations, but the probability is very small. Instead, in outliers, the probability of appearing is very high. Okay, so you are working, they are non-Gaussian, it's not non-Gaussian noise. When we speak about whiteness, it's a completely different thing. You are speaking about the memory of system from time to time. That's a completely different concept. Okay, so you can have outliers you can have a white noise and outliers. Okay.
Okay, thank you.
Because you can have non-Gaussian noise. So there is a common mistake that associates whiteness with Gaussianity. It's not true. Okay, you can have a white sequence which is not white, and vice versa. And you can have a white sequence that is not Gaussian. Okay. So whiteness has to do with the memory. We will speak more about this when we will speak about prediction and stochastic control. But bear this in mind, that whiteness has to do with the memory of the signal on itself. So the dependency, if you are at time 5, it is non-white if it depends somehow on what happened at time 4. Okay. Instead, having an outlier is to have, say, you are having at some time value, and this value could be a large deviation from its, a very large error can appear, and this appears with a high probability. Okay.
Okay, thank you.
Could you understand my explanation?
Yes.
Okay. More questions? Okay, so we stop today.
Yes.
Yes.
About the set of exercises that you have
in the Phoenix. Are there any solutions to those exercises?
No, in the set of exercises in the Phoenix, no. But you can find solved exercises in the exams. If you go to, well, I've posted a number of exams. Probably the exercises are not there, but you can easily find them by going to the corresponding years, to the previous years of the course of computer control, and the solutions are posted there, the solutions of the exercises. And I guess that most of the exercises have been are covered. I covered the solutions there.
Ok. Thank you.
Portanto, se forem ao Fênix aos anos anteriores, encontram sempre as soluções, porque eu publico as soluções sempre dos testes e dos exames e encontram lá. Reparem que eu às vezes engano-me a escrever a solução. Isso não quer dizer que faça as correções enganadas, porque às vezes até as faço a posteriori, mas uma ou outra, são erros que normalmente se notam. Se tiverem alguma dúvida, falem sempre comigo, está bem? Any other question? Okay, so we'll see each other tomorrow.
Thank you, Professor. See you tomorrow.
Bye.
Bye.